Hello, everyone. Thank you for joining this webinar. My name is Christian Dietz, and I'm super excited to present tonight's speaker to you. We'll be finding out about a tiny elusive particle, the neutrino, and ask questions about where they come from, how they fit into the picture of the universe, how we even know they exist, and how we build particle detectors to measure such a particle. So I'm very pleased to welcome you, Dr. Nicola McConkey. Thank you so much for joining us. Nicola is a lecturer at Queen Mary University of London, and she's an experimental particle physicist who spends her time developing technology to make precision measurements of one of the universe's most elusive particles, the one we'll hear about tonight, the neutrino. So we're not building neutrino detectors. She can be found folk dancing and playing music, including on one notable occasion, playing violin inside a particle detector at CERN. Now, I would love to hear more about that, but I'll leave it to you to ask questions, and we might end up talking about neutrinos all night. But with that, thank you so much for joining, Nicola. I look forward to hearing your talk and to discussing your work after this. Thank you.
Great. Thank you for the warm welcome. It's my great pleasure to talk to you tonight about mysterious neutrinos and where to find them. So today we're going to be talking about neutrinos. Firstly, I wanted to set the scene and talk about how neutrinos fit into our picture of the universe. And then I want to convince you that we really do know neutrinos exist, but I want to tell you how and talk about that. And then something that is dear to my heart as an experimental physicist, I spend my life measuring neutrinos. But I want to talk to you a little bit about some of the technology that we use and how we actually do measure these very elusive particles. And I wanted to then set the scene more broadly in terms of where do neutrinos come from and what can we use? Why is it useful to measure neutrinos? Okay, so let's start by setting the scene. How do neutrinos fit into our understanding of the universe? So everything in the world around us is made up of atoms, and those atoms are joined together to make many different elements which all have different properties. Now, this is the mainstay of nuclear physics, really. So this is the periodic table of elements, which you've probably seen before. It arranges elements in terms of the properties of the nucleus, and you know that elements that have similar properties are grouped together. So in particle physics, we look closer at what's going on within the individual atoms, and we try to break things down into what we call fundamental particles. So that means things that we can't break apart. We can't break them apart even more. So atoms, we know we can break them apart into smaller and smaller things. We're going to talk about particle physics, how we can break things down even more. So let's take a look at the atom. So in the atom, we have a central nucleus that's made up of protons and neutrons. So these are different types of particles. And the nucleus is positively charged, and it's held together by something that we call the strong nuclear force. And around the outside of this central nucleus, we have electrons that are orbiting the nucleus. And they're negatively charged. And so that means that an atom as a whole has an overall charge of 0, even though an electron and a positron, various constituents of the atom, they have positive and negative charges. Okay, but we can go deeper. So inside the nucleus, we have protons and neutrons. But if we want to break these down into their most fundamental parts, we can go even further than this. So protons and neutrons are each made up of a particle called a quark. So the proton has 2 up quarks and 1 down quark, and the neutron has 2 down quarks and an up quark. These are the 2 quarks that are most commonly found in the world around us, but there are many more different kinds. And the combination of quarks that you see in the proton and the neutron being different means that they have different properties. As we know, the proton has a positive charge and the neutron doesn't. So that's already one difference that you can see based on what it's made up of. So I'd like to introduce you to the standard model of particle physics. So you can kind of think of it like the periodic table of elements, but for particles. So we've grouped them into two main categories. So these ones are the matter particles, and these ones are the force particles. So the quarks that we've just talked about, they fit in up here. So the up quark and the down quark. And you'll notice that there are some other different types of quarks that are more exotic. They're actually heavier quarks. And they make up other proton-like particles that are called hadrons that typically decay very quickly and come back to what we see in the world around us, up quarks and down quarks. And down here, we have the leptons. So the electron should be familiar to you from everyday life. So it's a negatively charged particle. As we've seen, it surrounds the nucleus to make up an atom. But you'll also notice here that we have some other electron-type particles that we don't see around us. And you can kind of think of them as heavy electrons. And they also, like their quark brethren, they decay quickly back down to an electron or other particles. But you'll also notice that as well as these charged particles, so the electron, muon, and tau all have a charge of -1. You'll also notice that there are some other particles that are neutral. They are grouped one with each lepton, and they are the neutrinos. So you'll notice that each electron type charged lepton has a counterpart neutrino, and you can think of this neutrino as a kind of neutral electron type thing. Okay, so these are the matter particles. What about over here? But wait, there's more. So we have here all of the particles, and for all of the matter particles, there are also antiparticle partners. So antimatter. And they are very similar to the matter particles. They're kind of almost like what a particle would see as they looked in the mirror. So they share a lot of the properties, but in the electron case, the antimatter particle is a positron. And the positron has a positive charge. So they're the same but different. And we're gonna come back to antimatter in a minute. Okay. So I've showed you where neutrinos sit, and I introduced you to the whole particle family. Let's talk a little bit more about neutrinos. So we've said they have no charge. They're an electron. The electron neutrino is an electron type thing that has no charge. But what does that mean? How do they interact with the world around us? Well, neutrinos also have an extremely small mass. So they're 1,000,000 times smaller than an electron. And they are everywhere. They're very abundant. There are 100 trillion neutrinos passing through your body every second. How come we haven't noticed them? Well, it's because they interact only via the weak force. So they are very weakly interacting. They hardly interact at all. And over the course of your lifetime, on average, you might interact with one neutrino. So one neutrino might stop over the course of your whole lifetime. Maybe. So we have these tiny, tiny particles that are everywhere around us, not interacting very much. And I really like this Douglas Adams quote. So neutrinos are really small So they're these tiny, tiny particles. And so that means that the space between the atoms that make up your body looks like a vast empty space. So Douglas Adams said, so the chances of a neutrino actually hitting something, so like colliding with you, for example, as it travels through all of this howling emptiness in between all the atoms of your body, the probability is roughly comparable to that of dropping a ball bearing at random from a cruising 747 and hitting, say, an egg sandwich. So dropping a tiny, tiny ball bearing out of a plane that's cruising and hitting a particular kind of sandwich, it doesn't sound very likely, right? I haven't done the calculation myself, but one of my colleagues did, and he said it's ballpark about right. So it gives you an idea that neutrino interactions are pretty unlikely, but they do happen. Okay. Another thing that it would be remiss of me to not mention, although we're not going to have a chance to talk about it very much today, because it's a very interesting property, is neutrino oscillations. So you see in the periodic table here, in the standard model table here, that we've got 3 different kinds of neutrino. They're all neutral. They all each correspond to a different charged lepton flavor. And as neutrinos fly through space, they change type. So they change what we call flavor. And it's a quantum mechanical phenomenon that we don't really have much time to talk about in detail today, but it is one of the reasons that neutrinos are such an interesting particle to research. For one thing, neutrino oscillations might hide more different types of particle that we don't know about, and some of them might be dark matter candidates. And they also might help us to understand the matter-antimatter asymmetry in the universe. So what's that? Okay, so in the Big Bang, matter and antimatter were created from energy in equal parts. So for every matter particle that was created, an equal and opposite antiparticle was created. Positron, electron, neutrino, antineutrino, etc. But the picture looks very different now. So we are made of matter, and the universe seems to be made of matter too. So what happened? Where did all the antimatter go? We don't know. And by studying the behavior of neutrinos versus antineutrinos, we are trying to find clues that will help us to figure it out. Okay, so that's hopefully given you a little bit of background into neutrino phenomenology and why we're interested. Now I want to convince you that this tiny thing actually exists. And in order to do that, we're going to talk about 3 different concepts that hopefully you've seen before, but we probably haven't pulled them together in quite this way before. So beta decay, the conservation of energy, and the conservation of momentum. Let's start with beta decay. So beta decay is a radioactive nuclear decay whereby a neutron changes to a proton, emitting an electron and an antineutrino. And in this, the nucleus changes element, an isotope. So here is a Feynman diagram, which you may have seen before. It's essentially a conceptual picture for looking at how particles interact. And time goes this way. So we start with a neutron, and then the down quark of the neutron emits a W boson and turns into proton. And this W boson turns into an anti-electron neutrino and an electron. So that's what happens in beta decay. And so I wanted to give you a few examples of isotopes that decay via beta decay. So we have helium-3, which is tritium. We have carbon-14, which is used for carbon dating. And we have potassium-37, which can be found in bananas because there's potassium in bananas. Again, we'll come back to that later. Okay, so now let's talk about conservation of momentum. So you probably have an intuition for the fact that momentum is conserved because it's something that we experience in the world, right? Kicking a football, experiencing braking in a car, or the momentum of a cue ball being transferred to others in a game of pool, like is shown here. So in all of these cases, the total momentum is conserved. So the initial momentum is the same as the final momentum. Okay, and conservation of energy, again, the total energy in a system is always conserved. So in this example, we've got the kinetic energy of the train that's converted to potential energy as the roller coaster climbs up, and then the potential energy transforms to kinetic energy as the train speeds up as it goes down the track, down the hill. In particle physics, we have to consider the matter and energy equivalence. So you've probably heard of Einstein's famous equation E equals mc squared. So this relates energy to matter. So energy can be converted to matter, and matter can be converted to energy. So in this equation, we have energy, mass, and the speed of light squared. So the amount of energy that you need in order to make a mass is proportional to the speed to the mass and the speed of light squared. So that means that energy can be used to create new particles. I wanted to also add a caveat that there are lots of other particle physics conservation rules that we don't have time to talk about today. But yeah, this is a key point for today. Okay, now let's put it all together. Let's look at beta decay from an energy conservation perspective. So let's take the example of tritium. So we start with an unstable tritium atom, and it decays into a helium ion, emitting an electron and a neutrino. So tritium is an isotope of hydrogen that has 2 neutrons. And in the beta decay, one of the down quarks changes to an up quark as the neutron changes to the proton. So that means that the element hydrogen changes to helium. Now, initially, scientists had no idea about the existence of the neutrino, but they did know that an electron was emitted during beta decay. So to them, it looked like this: no neutrino, tritium decaying into a helium and an electron. So let's discuss what you would expect to see in an experimental observation of beta decay as per this diagram. So this is what scientists knew in the early 1900s. So what have we got from the perspective of conservation of energy? We start with a tritium nucleus. We end up with a helium nucleus and an electron. And using E equals mc squared, we can calculate how much energy is needed to make each of the particles. So we need energy to make this, and we need energy to make these. Okay, now in the process of beta decay, because of nuclear binding energy, which I think you heard about in a previous building blocks lecture, we have energy released in the beta decay, and we can actually calculate that theoretically. We know how much energy that is. So when we're doing our experiment, what we can do is make sure that tritium is at rest. And that means that it has no kinetic energy or momentum. Okay. So the energy that we start with is the energy needed to make a tritium nucleus and this beta decay energy. And the energy needed to make the helium nucleus and the electron is smaller than this total, which is good because it means the interaction can actually happen. Because if it was energetically non-possible, this interaction would not happen. but there's more energy over here than there is over here. And that means that all of the energy has to go somewhere because of conservation of energy. So the remainder of the energy gives the daughter particles, the helium and the electron, some kinetic energy. Now, remember that the tritium was at rest. So that means by conservation of momentum, these two particles must be emitted back to back. So since the nucleus is really large compared to the electron, that means that the electron will be emitted with a really high velocity away from a slightly recoiling nucleus. So in the early 1900s, various scientists set out to measure the kinetic energy of this electron coming out of beta decay. And since this calculation that we just showed, it would hold true for every single beta decay, they expected to see electrons coming out with one single energy every time. So yeah, they expected to see electrons with the same kinetic energy every time. And this graph shows what they did see. So the expected monoenergetic electron energy was completely different from what they actually saw. They saw electrons of lots of different energies, but they were all less than what they expected. So what do you do in this situation as a scientist? So you question everything, right? Maybe we messed up the experiment. Let's try it again. Several people tried this again. They measured the same thing. They noticed that this was a very nice continuous spectrum. They measured it very precisely. Okay, so maybe energy conservation isn't correct. Maybe energy isn't conserved. Maybe momentum isn't conserved. Another thing you can do is come up with another theory as to what might be going on. So in 1930, Wolfgang Pauli suggested another solution. Maybe there's another particle emitted in beta decay that we just can't see. So as an experimentalist, this is challenging, right? So we've been doing all these experiments, and a theorist comes along and says, oh, there's something else coming out of the interaction that you just can't measure it, sorry. You think of that as a challenge. And so it wasn't broadly accepted in the community for a little while. But eventually, after 20 years, we experimentally observed the neutrino for the first time, and Pauli got a Nobel Prize. Okay, so let's revisit our thought experiment, and this time include neutrinos. So the initial state is identical. And the first thing that's different is that we need the energy to create the neutrino in the final state. But also, both the energy to make them and the momentum are split 3 ways rather than 2. And that's why we see this spectrum of electron energies. So it's because some of the kinetic energy has gone to the neutrino and some has gone to the electron, and a small amount has gone to the helium nucleus. So actually, experiments today are measuring the beta decay very precisely still in order to determine what the neutrino mass is. And that includes one experiment that I work on, which is called Quantum Technologies for Neutrino Mass. Okay, so hopefully by this point, I've convinced you that neutrinos exist. But we also know that they don't interact very much at all. So how do we measure them? Okay, I'm going to start from a different perspective. I'm going to start with how do we measure particles, because that is a much easier place to start from. So how does a particle detector work? Essentially, we have a particle detector. We have an incoming particle that comes into the detector from, a beam source, a radioactive source, from cosmic rays. A particle comes into the detector and it leaves energy behind from its interaction. And then what we do with our particle detector is we measure how much energy was left behind. And we do that by seeing how the particle detector has changed. So we see the charge that's left behind, we see the light that's left behind, or we see the heat that's left behind. The heat one is really hard, by the way. We have to have there are detectors that are just above absolute zero, and they can detect when an interaction has happened because there's a tiny amount of thermal energy that's been transferred to their detector. So we don't normally talk about those. We normally talk about the other two, but it's quite fun to know that that is also an option. So by measuring the energy that's left behind, we can identify, or we try to identify, what the particle interaction was. So I said that charged particles leave a signature behind in the detector. And each charged particle leaves a different signature behind in the detector, a bit like footprints in the snow. But you also remember that neutrinos are not charged particles, they are neutral. So they leave no footprints in the detector. And that means that we can only see neutrinos once they've interacted in the detector and produced some charged particles that we can see. So, like for example, in this Feynman diagram, which we'll talk a little bit more in a minute. So you'll see that in this neutrino interaction, we do have a charged particle coming out, and that's what you look for. So in our particle detectors, what we look for is a gap followed by a bunch of charged particles. So this is where a neutrino was. And you'll notice that all the footprints are going away from this point that we call the interaction point. So what does this look like in our detector? So in this Feynman diagram here, we've got a neutrino coming in and interacting with a neutron, which is part of one of the atoms that makes up the neutrino detector. So what it looks like in my detector is this. So the neutrinos are coming from the right in this image. You see this big gap. And then this is what an electron looks like in my detector. We actually also have another proton in this interaction, because this Feynman diagram shows the most simple of cases. And actually, when you're interacting with all the molecules in a detector, you often get more interactions in the nucleus and lots of different particles coming out, like in this case, a proton. So I wanted to say that the probability of a neutrino interacting is minuscule. So what we have to do in order to actually measure neutrinos is build large enough detectors that neutrinos are likely to stop in the detector. So there are lots and lots of different kinds of particle detectors, and some of them are designed to measure interactions that we know extremely well where we're going to happen. So for example, at the Large Hadron Collider at CERN, they collide beams of protons, and since they have very fine control over these beams of protons, they can make them interact at one particular spot, and they know exactly where that's going to be, and they can build their detector around it. And sometimes these detectors are called onion detectors because they have lots of different layers, and each of the layers has a different job to do in terms of measuring the particles coming out of the interaction. And they're very, very powerful detectors, but they're not very good for measuring neutrinos directly. Why is that? Because we have no idea where the neutrino is going to interact. It might stop here, it might stop here, it might stop here, it might not stop at all. So they very rarely interact. And in order to increase the likelihood that a neutrino would stop, we need to build a big detector that is pretty uniform throughout. So this is one of the biggest neutrino detectors in the world, Super Kamiokande. It is in Japan, and it is a big tank of water. It's 50,000 tons of water. And at this point, I wanted to introduce the whale for scale. So blue whales are about 25 meters long, and we could fit one in Super Kamiokande. Okay, So neutrino detectors are the giants of the particle detector world. And that is because if you have more target mass, you're more likely to stop a neutrino. But having more target mass is also more expensive. And because we live in the real world, that means that we have to choose a material that is cheap and available in large quantities. So here are some options on the table. Water or ice. Water is quite cheap. I just showed you a detector that was made of water. This is Ice Cube, which uses the actual Antarctic ice that's instrumented with light sensors to measure high energy neutrinos that are produced in the galaxy. This is my detector, the short baseline near detector, SBND. It's made of liquid argon, and it's an experiment that I've been working on for the past 10 years. And the detector is quite a bit smaller than the other two because it's actually very close to a beam of neutrinos. But as we speak, SBND is measuring neutrinos, and our goals are to understand more about how neutrinos interact with matter and also how many different kinds of neutrinos there are. And I could talk lots more about SBND and how the detector works and how any of these detectors work. So please ask me about it if you're interested. Another good option is liquid or solid scintillator. So that's something that makes light when the particle goes, when energy is deposited in it. Neither of these detectors are actually operational anymore, but both of them are made out of scintillators. The whale for scale coming in here. I told you this was a smaller one. There we go. So making these huge detectors obviously needs a lot of physicists, but we also work very closely with engineers and technicians that help us to design and build the best possible machines for measuring particles. Okay. So there are three flavors of light neutrinos. I just want to quickly show you what they look like in our detector. So this is an electron neutrino as it looks in SBND and as it looks in Super Kamiokande. So you can see that if you're using water, the way that the detector works is quite different. Yes, I don't have time to talk very much about it, but essentially you can see that a muon neutrino looks very different to an electron neutrino in both of these detectors. Now, the third neutrino flavor is a bit special because it decays incredibly quickly. So it has a lifetime of 2.9 times 10 to the minus 13 seconds. So that means that they've decayed already before you can measure them. So you need specially designed detectors to see this level of precision. And actually, this is taken from a detector, the Opera experiment, and it is it's essentially lots and lots of sheets of emulsion, which is basically like camera, like an pre-digital camera film. Lots and lots of sheets of film, and each one of these dots comes from a different sheet of film, and the precision has to be well, you can see here it's 100 microns is this scale. So they decay quickly, so you have to be able to tell the difference between these vertices. Okay, so I've talked about how we measure neutrinos. I want to finish off by telling you a bit about where neutrinos come from. So anywhere there's a beta decay, there's a neutrino. So I mentioned that there's potassium in bananas. That means that some fraction of that potassium is potassium 37, and there are neutrinos coming out of a banana. The dose that you get is very, very small. It's about 100 times smaller than the radiation dose that you'd be exposed to normally over the course of one day. But there's quite a fun way of measuring radiation that's called the banana equivalent dose. So I'd encourage you to go and look that up if you're interested in radiation measurement. But as well, I wanted to encourage you to look up a YouTube series if you're interested in finding out more about neutrinos. One of my colleagues, Kirsty Duffy, has a YouTube series called Even Bananas, and it's all about neutrinos. Okay, so bananas, great. Nuclear reactors, also lots of beta decay going on there. So they're an excellent source of neutrinos. But also uranium and thorium, those decay chains have beta decays in them. So the uranium and thorium in the Earth's crust are giving out neutrinos. And this is really cool because neutrinos can pass through almost everything without reacting. And so we can use them to measure places that we otherwise couldn't get to. So we can use neutrinos, they're called geoneutrinos. We can use geoneutrinos to understand the composition of the Earth's crust. So neutrinos are also produced in nuclear fusion reactions. So in nuclear fusion, for example, hydrogen fusing into helium, you have a proton changing into a neutron via beta decay, and the proton and neutron make up the next heaviest nucleus. And that means that we can learn about the processes that are going on in the sun by measuring the neutrinos that are coming out of the sun. And also supernova neutrinos. So neutrinos are produced via inverse beta decay when stars explode. So 99% of the energy that is coming out of a supernova is actually emitted as neutrinos. And these visual images that you associate with, they come from the light. So a fraction of the other 1% of the energy that's coming out of the supernova. But because there are so many electromagnetic interactions happening in the supernova, the neutrinos will reach us on Earth first because they don't interact with anything on the way. So all the light is scattering, having a lot of electromagnetic interactions. Neutrinos, they're gone. And that means that we can work together as a field. So we have a network of neutrino detectors that are constantly on the lookout for neutrinos from a supernova. And that means that if we see a signal, then we can communicate to the astronomy community and say, hey, you should point your telescopes over there because there's going to be a supernova. And that network is called SNOOS, Supernova Early Warning System. And thus far, we've actually only seen one supernova, 1987A, but we're hoping that there'll be another a supernova that is near enough that we can see something in our neutrino detectors, because there's a lot online at the moment. So yeah, one of the things that really amazes me about neutrinos is that even though there are so many mysteries about them, we don't know their mass, we don't know why they interact so little, there are lots of things that we don't know about neutrino oscillations, we can still use them to learn about the universe. So we've measured so many different kinds of neutrinos. Neutrinos from the galaxy, neutrinos that we've made ourselves in accelerators, neutrinos that have been produced in the atmosphere, neutrinos from the sun, nuclear reactors, and from the Earth. And we still don't know so many things about neutrinos, but we can still use them to learn about other things. So today, in summary, we talked about some of the properties of neutrinos. We talked about how we first figured out that neutrinos existed. We talked about how you detect neutrinos, and we've talked about some of the places that neutrinos are produced. That's all I have for you at the moment, so thank you very much.
Thank you so much, Nicola. It's fantastic to hear your talk. Before we move on with the questions, I wanted to introduce you and everyone else to an additional panelist in the room for asking questions of you, Dr. Elizabeth Cunningham. Elizabeth has actually worked across nuclear physics, my field, and particle physics, Nicola's field, for years. I'm very pleased that we have Elizabeth here to ask a range of questions of you, Nicola. But from my perspective, just to give a personal view, I think this is amazing. I think neutrinos, from personally, the neutrinos was the biggest revelation for me over the course of my academic career and studies. If I can mention one thing, that was neutrinos. It's not actually what I spend most of my time working on, but it's probably the part of physics that excites me the most. So thank you so much for sharing all of that, and I'll shut up and hand over to Elizabeth for managing and sharing all of your questions. Thank you so much.
Thanks.
Yes, thank you, Christian, and thank you, Nicola, for that wonderful talk. Yes, neutrinos is a really exciting area of physics, and I'm not going to waffle on too long because we have some really, really great questions that I want to get straight to. So if you're happy, I'll begin with the questions. So I think we have some from towards the beginning of your talk. So the first one is, how did we estimate that we would only interact with one neutrino over the course of our life?
That is a great question, and it is very ballpark because obviously, you know, different people have a different mass, different people live for different lengths of time, and also different types of neutrino, different energies of neutrino have a different probability of interacting. So in a very so the interaction cross section of a neutrino is around 10 to the minus 34. So that means that the probability of a neutrino interacting, your average neutrino interacting is around 10 to the minus 34. And the calculation was done kind of bearing in mind that number and the average size of a person and average life. Yeah.
Very good. Thank you very much. Someone else asked towards the beginning, how do we know that the force particles exist?
That's a really great question. I always find it quite hard talking about the force particles because they are less tangible in some ways than the matter particles. But one really easy example is to talk about light. So the photon is the exchange particle for the electromagnetic interaction, and that is one of the bosons. But there have been a lot of I can talk a little bit about the experiments that allowed us to measure those particles. So they were theoretically proposed as ways for the matter particles to interact with those with the different forces. But one of the ways that that they were first measured was by colliding particles. So the predecessor to the LHC was called LEP, Large Electron Positron Collider, and they measured the mass of the Z boson very precisely. So what they did is they collided electrons and positrons, and they found that with the energy that was created in that annihilation, they found these particles were created, and they observed their decay to various different particles, and it fitted the theory very well. So that's an example of how we as experimentalists would verify and check pieces of that theory.
Okay, thank you very much. And then I think another one's probably prompted by looking at the Standard Model was, what is the Higgs boson and why is it by itself in the table?
It's by itself in the table because unlike the other bosons, it's more complicated to explain. It's a scalar particle, and the others are vector particles. So it's the Higgs boson isn't a force mediator in the same way as the others. So the other three forces that are shown in the table, so the weak interaction, the electromagnetic interaction, and the strong interaction, their mediator bosons are all grouped together. But the Higgs boson gives particles mass, so that it's not the same type of field as the other fields. So it's not interacting with a force in the same way, which is why it's kind of off to the side there.
Very good, thank you. So I think your talk, obviously, neutrinos has captured a lot of people's imagination, and now they're looking for them as answers to all the questions in cosmology. Someone has asked, how far do neutrinos travel, and can they be used in a similar way to the cosmic microwave background radiation?
Great question. So neutrinos will just keep going on forever. We haven't observed neutrinos decaying, so that means they will just keep going until they stop or interact with something, which is less likely. And the link to the cosmic microwave background is really interesting because we can measure cosmic neutrinos that are left over from the Big Bang, and one of the things that's a little bit exciting in the field at the moment is the fact that we're trying to measure what the neutrino mass is. We don't know what it is. I mentioned measuring beta decay is a way that you can directly measure the neutrino mass. It's really difficult to do it that way, but we're doing it anyway. The astronomers like to sum over all of the energy that they can see in the night sky. So you may have seen the beautiful images from Planck, which shows the cosmic microwave background, and they have done the astronomers, cosmologists have done calculations of what the total mass of neutrinos in the universe must be, based on looking at those images, and it's actually it's in tension with the other measurements, which is very exciting, because when things are unexplainable, then, as I said in the talk, like, what do you do? How do you deal with that situation? So it's an exciting topic in the field at the moment.
Yeah, that's where the interesting science happens.
When
Wonderful.
wrong.
Exactly.
Yeah.
Although you never want to be the one that gets it wrong. Yes. So someone else. So that was talking about cosmic microwave background. Someone else has asked around. So neutrinos were proposed in 1930, discovered explicitly in 1956. So if we could discover neutrinos, why can't we detect dark matter?
Well, so I said that neutrinos were very weakly interacting, and we neutrino physicists think of ourselves as rare event physicists. So we measure things that don't happen very often at all. Dark matter is next level. So what the problem, the difference between neutrinos and dark matter in terms of making measurements is that we know that we have sources that are producing neutrinos at the moment. So we can make a beam of neutrinos. We know that neutrinos are coming from every beta decay. And I guess in the 1950s, like, they didn't know this, but they were trying. It was their guess. Like, they were trying to measure neutrinos from the sun, and it turns out there are neutrinos coming from the sun. So they were able to see them. Dark matter, we have some ideas of what sources of not dark matter are, but we don't know how they interact with matter. So dark matter could also be passing through us every second, but not interacting with us. So the clue is really in the beta decay, that we'd seen something that could be explained by them, and the interactions with dark matter. There are phenomena, but we haven't. We keep
even less.
Yeah, yeah. We're still looking.
There's obviously what your talk has prompted a lot of people's interest and imagination around cosmology, because there's lots of sort of probing questions around this. But it's very tricky. If we go back to sort of more the mechanics of neutrino detector, someone was interested in what is a scintillator, but also interested in you. So what developed your passion for particle physics and your interest in neutrinos?
Okay, so let's take the first one. So if you have an atom, if you happen to give that atom some energy, it might get excited. So an electron might jump up to a next energy level, and so you have an excited atom, and then when it falls back down to its normal state, that energy has to go somewhere. And that energy is often emitted as a photon. And that photon is what we call scintillation. So there are some types of materials that are really great at doing that. So if you put some energy in, they give you a lot of light. And that's what you look for in making a scintillator detector, because you want to be able to be sensitive to a tiny amount of energy being deposited in your detector. So you pick a material that will do a really good job of telling you about that. So how did I become interested in neutrino physics? Well, I was an undergraduate in maths and physics. So I didn't actually get to do any lab work at all at university. And I did a summer project. So I managed to get a summer internship working in a lab with one of the lecturers. I was at Warwick University, and I was building stuff in the lab, and it was the best thing ever. You know, I was going to the lab, we were putting things together, we were seeing if it worked, and just that curiosity and the drive to make something that worked, but break it down into all of the steps. That's a thing that made me really like research. And neutrinos are quite compelling in terms of measuring neutrinos, finding something that is difficult to do, trying to make a new kind of neutrino detector, trying to make an existing type of neutrino detector work as well as we possibly can, so that we can probe this physics, so that we can understand what's going on in the universe. Yeah.
Very good. Thank you very much. So there's loads of questions, so we're not going to get to them all, but there's a few questions on antimatter. So I think we'll just finish maybe talking about antimatter. How do we know that there's more matter than antimatter? Like, how do we know that all the antimatter isn't just hidden somewhere? We can't find it.
That's a great question. And I think that this, so on a terrestrial level, I think we can be pretty sure, right? So like we know how matter and antimatter interact. So you would get annihilation, so you'd get a lot of energy, which would be chaotic, and not something that we observe. But in the visible universe, we haven't seen things that look like they're interacting as matter and antimatter colliding and producing this light either, and producing this energy either. And so I'm not a cosmologist. I'm not an astrophysicist. So you'll have to take my hand-wavy explanation. But the phenomena that we have observed are not consistent with there being antimatter off somewhere over there. Yeah.
Okay, I think I think the question is just if it was, where's all the energy? Because it would have all annihilated us.
Yes. Yeah.
So I think you're exactly right.
Thanks.
So then someone's asked about antineutrinos. So what are antineutrinos, and do I remember them being emitted in a kind of beta decay?
Yeah. So, what are antineutrinos? That is a fantastic question. And the reason it's a fantastic question is because something that I didn't mention, which is the question as to whether neutrinos and antineutrinos are the same, in fact. So, everything that we've talked about, in particle physics, we're really keen on conservation of stuff. So we talked about conservation of energy and momentum, but we also like to conserve the numbers of things in an interaction. So the number of leptons. So in a beta decay, we had a neutrino and an electron coming out, but an electron has a lepton number 1. It's a lepton. A neutrino also has a lepton number of 1 because it's a lepton. But antineutrinos and anti-electrons, they have lepton numbers of -1. Because we started out with none at the beginning, we want to end up with 0. So that means that in the beta decay, we need an electron and an antineutrino. So that's where the antineutrino came from. So when I mentioned antimatter, I talked about how the properties are almost like looking in a mirror. So for in the same way that like +1 and -1 add up to 0, if you had a neutrino and an antineutrino, it would add up to, well, some energy, but nothing in a lot of these senses. So that's why I was very remiss in some ways about talking about neutrinos and antineutrinos, and that's because I wanted to talk more about like the phenomenology of how neutrinos broadly interact and antineutrinos and neutrinos. We want to know how they interact differently. That's one of the big questions in neutrino physics. I'll maybe come back to what I said about neutrinos being their own antiparticle. That is something that we are trying to test. But there's a theory that neutrinos might be a Majorana particle, and that is their own antiparticle. And we're trying to measure whether that is the case by a process called double beta decay. And we're trying to observe if that could happen with no neutrinos emitted at all. And that could happen in the instance that a neutrino is its own antiparticle, so they annihilate inside the nucleus. So yeah, it's a very interesting question, but for the moment we kind of we talk about neutrinos and antineutrinos as different things because of the way that they interact and this symmetry and conservation.
Thank you very much. I think there's loads more interesting and probing questions, but I think we're going to have to leave it there. I think that's the thing with the most exciting areas of science when you're really at the cutting edge. You know, these have been really insightful and probing questions, but these are questions also that scientists are asking themselves and we don't have all the answers to. So thank you very much for so eloquently summarising what we do know and answering these questions. It's been really wonderful talking to you. Thank you. So this is our final. It wraps up the Nuclear Masterclass webinars, but this is not the end of your opportunities to interact with exciting physics going on at York. So the University of York offers a regular webinar series that you can book online. Thank you again to Nicola for such a wonderful talk about such an exciting area of science. Thank you all for coming, and we hope to see you at the future York online events. Thanks everyone. Good night.